Good evening. I hope you had a productive test. Hope you all get good grades, and if not, it's about time you learned this stuff. It was on Strumioville, right? Wasn't? Separation of variables, okay. So we've done that kind of stuff as well, so you should be masters. If not, I can give you more homework and you become better. And
actually, quantum really helps.
See? For today, it's time to solve a very important example, the harmonic oscillator. It's the most important example of quantum mechanics and pretty much of all of physics. From today on, you're going to meet and re-meet the quantum harmonic oscillator all the time. It's going to appear everywhere. Sure, you don't understand exactly what I mean about this now, but when you see it again during your master, during your doctorate, and so on, during your third year in your bachelor, remember that I said you'll see it all the time, which is why this is a very important example. It's discussed everywhere in the books. We're going to talk about this for 2 weeks in a row. So today we're going to talk about the Eigenstates, Hermite Polynomials, how to deal with the harmonic oscillator in position space and momentum space. And then next week, well, not next week, in 2 weeks, because next week is Hanukkah, so there won't be a lesson. But in 2 weeks, we'll discuss what you've seen in class yesterday, the raising and lowering operator, A and A dagger. So we're going to have a whole separate tutorial on that, because these things are very important, not just for this course, but for the rest of your physical life. So your life in physics, physical life. Okay, so let's go ahead. Any questions before we start? One more thing, because there's no class next week, you have 2 weeks for your homework, because it doesn't make sense otherwise. But because you have 2 weeks, I'll be very unhappy if people don't finish on time on extensions, because you have 2 weeks. So double the time means half the complaints, right? Okay, quantum harmonic oscillator. Let's first of all define the problem. So we're talking about a potential you can basically think of some particle tied to a spring with some spring constant k. Now this is very confusing because we use k for the momentum. H bar k is the momentum. This is not the same k. So this is very confusing, which is why we want to get rid of this k in the expression for the potential, so we don't get confused with the momentum k. So what we'll do is we'll use the Eigen Frequency, the Eigen mode of the harmonic oscillator, which I hope you know is root k over m, where k is the spring constant, m is the mass. So if you plug this back into here, right, k equals m omega squared, you can write the potential as 1/2 m omega squared x squared. So this is the way you're used to writing the potential of an harmonic oscillator from first year. From now on, this is how we write it. So the strength of the potential is now defined by omega. The stronger omega, the larger the frequency, the stronger, so the narrower the potential well. And this way you won't confuse it with the k from the momentum, because it doesn't exist anymore. Okay, that means that we can now write down the Hamiltonian. So the classical Hamiltonian remember, it's just the sum of the potential and the kinetic energy in terms of x and p. So it's the potential term p squared over 2m plus this potential. In order to make this quantum mechanical, so we want to have a quantum mechanical operator, the Hermitian operator. So all we have to do is replace the momentum by the momentum operator and the position by the position operator. And we can now write this in any space that we want. We can write it in position space, or momentum space. All we have to do is plug in the operators, which are well known. This procedure is called canonical quantization. It's the standard way to turn a classical theory quantum. Of course, you're not doing this for the first time. Just want to go over it again. Before we go ahead and actually look at the solutions of the operator of the eigenvalue equation, let's analyze the Hamiltonian on a more basic level. What we want to find, let's also as an example, it's an exercise, we want to find the average energy, the minimal average energy, such that the uncertainty principle between P and X is satisfied. Such that, ST is such that delta X, delta P equals H bar over 2.
What is the ST?
Such that, find the minimal energy, such that delta X, delta P equals H bar over 2. Let's start solving the problem. You'll see what I'm getting at. So the average energy, right? How do you find the average energy? It's the average Hamiltonian, right? So you take the average of the Hamiltonian. So we'll just take this operator. We'll take the average. So it's the second moment of the momentum plus the second moment of position. So you know that the uncertainty is related to the second moment, right? Delta x squared, say, is x squared minus x squared. And the same goes for P. So you can interpret the second moment of momentum more or less like the uncertainty, and the same goes for the second moment of position. So there must be some trade-off, right? It's the sum of the uncertainties. So just making one of the uncertainties 0, and then the other becomes infinite. So the energy will be very large. So you need to find some trade-off between the two uncertainties in order to minimize the energy. This is how we'll be able to find the minimal energy that is allowed by quantum mechanics. Right? In classical physics, we'll just say the minimal energy is 0. It's just the bottom of the well. But because there's the uncertainty principle, you cannot minimize the uncertainty in both position and momentum simultaneously. That constraint causes the lowest possible energy, called the ground state energy, to be non-zero. It's a direct consequence of the uncertainty principle. So let's actually solve this. So I'm going to plug in these relations into here. So we get delta P squared minus average P squared divided by 2m. Plus the potential term okay, so all I did is I plugged in the second moment. It should be a plus, right? I had some mistake last year already. I'm repeating mistakes. It's great. That also makes sense. Great. So I plugged it in, and now because I'm adding something, this must be larger or equal to the same thing without the average. So if the average position, average momentum is 0, then it's equal. And if they are non-zero, but they must be positive, this number it's a square or something, so it's this, so it must be positive. So this must be larger or equal than this. Now you see exactly what I talked about. This is the sum of the uncertainties, the uncertainty squared. So minimizing one and making the other infinite will not cause this energy to be minimal and cause the energy to be infinite. I want to find some ratio between the two so that the energy will be minimal. In order to do this, I'm going to plug in the minimal uncertainty. So I'll use the uncertainty relation, and I'll divide by delta P, and then plug this into here. So this will be equal to delta P squared over 2m plus m omega squared divided by h bar squared divided by 8 delta P squared. Right, and you take the square of this and then plug into here. So you see that the energy as a function of the uncertainty momentum, this term increases and this term decreases as delta P grows. So again, you see there must be some minimum to this function, and this is the minimum we want to find. Find the minimum of E as a function of delta P. So in order to do this, I need to take the derivative with respect to delta P and make it 0, and this will give you the minimum. Right? That's how you find the minimum. Is it clear what I'm doing? Is the idea clear? So I'll take the derivative of this. So what we get is delta P over m minus 2, which goes over the 8, it gives you a 4 downstairs, delta P to the third, and then there's an m omega squared h bar squared. This is to be equal to 0, as we said. So all I have to do is get delta P from here, and we find that delta P is root m omega h bar over 2. At home, check that indeed the square root of the mass times the frequency times h bar actually gives you units of momentum. That's something I would check if I were you. I wouldn't just believe it. I'm going to make one more definition. I'm going to define something I'm going to use later, which I'm going to call sigma p. This sigma p I'll define as root 2 times the uncertainty in p so that's just the constant without the numerical value. Another thing we can do is plug delta P back into the uncertainty relation, into here. If we plug it back into here, we can also find delta X. So delta X turns out to be the root of h bar over 2 m omega. Here again, check that this actually gives you dimensions of a length. This must be in meters. Something else I would check. And equivalent to the momentum, we also define sigma x as root 2 times delta x, which is root h bar over m omega. The sigma x and sigma p, we're going to meet them in a couple of minutes again, but they are typical length scale in position and momentum space. So we'll be using them. But this is, for the moment, this is just a side remark. What we actually want to do is find the minimal energy. So what we have to do is take the minimal delta P. So the delta P, that minimizes the energy, right? That's this. This is the delta P that minimizes the energy because it satisfies this equation. So if you plug that back into E, so we plug delta P back into the average energy, which is this expression. And when we do so, we find that E is greater or equal then, right? It's greater or equal. So plugging in the first expression, right? The M cancels, and we're left with h bar omega over 4. And then we take the square again, but now it's downstairs. So we get again h bar omega over 4, and this is equal to h bar omega over 2. So we see that this is our potential well. This is our potential well.
That's the ground state energy, right?
It is exactly ground state energy. So let me just get to the point. This is our potential well. The potential has a minimum at x equals 0. The potential is equal to 0. So a classical particle could be at x equals 0 and not move, so have 0 energy and not oscillate, right? A classical particle can do that, but a quantum particle inside a potential well must be here. So it must have some motion. It must move, it must oscillate. It cannot just stand still at the bottom of the well. And this is one of the great discoveries of quantum mechanics. There is no such thing as a particle inside a harmonic well with 0 energy. It doesn't exist. The minimal possible energy is h bar omega over 2. And if you remember from the lecture, indeed the ground state energy is exactly equal to, not greater than 2, but equal to h bar omega over 2. So actually the ground state energy is exactly the minimum imposed by the uncertainty. If it would be larger, it wouldn't be surprised. It could be larger as well. This is the minimum imposed by the uncertainty principle. Questions about this? All right. Okay, now after we understand the Hamiltonian, we understand the reason we could actually do this calculation so easily is because both the momentum and position are quadratic in the Hamiltonian. It's x squared and p squared. That's why this analysis could be done so easily. Well, it wasn't easy at the time. This was one of the great achievements of Dirac about 80 years ago. It looks simple now, but this was a great achievement 80 years ago. That was before the Schrödinger equation. This was already found. It's a historical anecdote. But now we can actually go ahead, use the Hamiltonian operator, and find the eigenstates. Let's find the eigenstates. We know that the general solution I'm just repeating stuff you know already. The general solution is an infinite sum over the eigenstates, because it's a well, we're expecting discrete eigenstates, which is why it's a sum, not an integral. So we know that already. And we know that in order to find these eigenstates, phi n, we have to solve the time-independent Schrodinger equation and all of these solutions will be there's an infinite set of pairs phi and En that solve this equation. And as soon as we found them, we can plug them back into the infinite sum and use initial conditions to find Cn. Okay, so let's first of all do this in position space. I will not go through the entire calculation that you did in class. Obviously that was took a long time and there's no point of me repeating it. I just want to stress a few points. So if we use the Hamiltonian operator, let's write down this equation in position space. So there's a second derivative, and then there's the potential. I'm going to take the energy to the left-hand side and multiply the entire thing by 2m over h bar squared, just to get it in some standard form. So it's a homogeneous one-dimensional differential equation, ordinary differential equation. This term here, the coefficient of x squared, that looks familiar, right? We have it up here, it's sigma x to the fourth actually, because it's the root up here. So it's sigma x to the power of 4. And I'm also going to manipulate this coefficient, the coefficient of E, in order to put in the sigma x. So there's a lot of algebra involved, but I'm going to come right to the conclusion. Which is this. So I've now used the typical length scale. I always said sigma x is typical length scale. I haven't shown it to you yet, but I will in a second. But I've incorporated it into the differential equation. Now this is the equation that you solved in class. It took you a little while, and you looked for an asymptotic solution. What happens when x goes to infinity? You found the Gaussian. And then you solve the remaining equation by plugging in a Taylor series, and you find the recursion relation, and so on. And after you worked hard, you found the eigenfunctions. So let's write them down. So you found that the eigenfunctions phi n of x, there's some long, ugly normalization constant. So it's 2 to the power n times n factorial times the root of pi, and take the root of everything. And then there's a 1 over root sigma x. We're dividing by this length scale. And then we have two functions. The first one is something called a Hermite polynomial. The argument of the polynomial is dimensionless. It's x over sigma x, so this thing carries no units. And the second function is a Gaussian where again sigma x is the standard deviation, right? It's the width of the Gaussian. And that's why I called it a typical length scale. It's a typical length scale because it's the width of the Gaussian. The width of the Gaussian packet, the surrounding of this wave function. Note also that the only thing actually carrying units here is this, the 1 over root sigma x. Everything else dimensionless. So you see right away, since sigma x is a length, so the root is one of the root of a meter, which is exactly the units you would expect for a wave function in one dimension. So this is where all the units are. The second thing that you found from here were the energies. The energy levels are h bar omega n plus 1/2, where n starts from 0 this time. So for n equals 0, you get the ground state energy, h bar omega over 2, and then each additional energy level adds a portion of h bar omega to the energy. We spoke about this, so you see that the energy levels are equally spaced. Unlike all the other examples we've seen so far, potential wells, finite, infinite, was never equally spaced. But in this example, that's one of the reasons that your harmonic oscillator is so important, and it will be in your future in physics. The reason that the spectrum has such a nice, is so nicely equally spaced, makes it very useful to incorporate in many problems in physics. Note that sigma x is a purely quantum mechanical quantity. First of all, it has h bar in it, which automatically makes it quantum mechanical. Also, sigma x is a measure of the non-locality of the particle. Because the wave function, the physical extent, the width of the wave function is more or less sigma x. So sigma x is the measure of non-locality of the particle, which makes it a pure quantum mechanical thing. Because not being local is something quantum mechanical. Let's repeat this game. Let's repeat what we're doing, what we did in position space, now again in momentum space. So I want to write down the Schrödinger equation again, but this time I want to write it down in momentum space. So now the p operator is just multiplication by p, and the x operator is a derivative with respect to the momentum. So it's p squared 2m times phi n tilde of p minus 1/2 m omega squared h bar squared phi n of p double prime. The derivative is now in the potential term, and the kinetic term has Chisholm multiplication. It's exactly the opposite. And that needs to be equal to the energy again. I will move stuff around to get it into the form where I first have a derivative and then all the rest. So it will be apparent that this is an ordinary differential equation, which is homogeneous. Sorry, I'm jumping ahead of myself. So you already see the similarity to this equation. This is a momentum space, this is a position space. But you already see that it has a very similar form. There's a second derivative, then some constant times the energy, and then minus some constant times the variable squared. Here it's p and here it's x, times the function. And also here we recognize again the sigma p. This time it's sigma p, not sigma x, obviously. This is sigma p to the power 4. That's exactly our definition. So we can again incorporate this definition And we get this equation. The solution to this equation, of course, you can do the same way as you did in class. Once again, look for a solution in infinity, plug it in, use a Taylor series, find recursion relation, and so on. Or you just look at these two equations, note that they have the exact same form, which means that they have the exact same solution. Just that the variable here is p. And instead of sigma p, instead of sigma x, you have sigma p. So phi n tilde of p is this function, and of course the energies, which you also find by solving this, are of course also exactly the same. So what have I tried to show to you here? Usually when I ask you, I tell you this is the wave function or the eigenstate in position space, and now I want to know it in momentum space, then usually when you say, oh, that's simple, I'll just take the Fourier transform. So you take this function and you plug it into the Fourier transform, right? You multiply by e to the ikx and take the integral over x, and you get a huge shock. Because I can take the Gaussian, I know how to transform. But this is a polynomial times the Gaussian, which means we're integrating by parts n times. So for n equals 1, it's easy. For n equals 2, it's easy. But what about n equals 5? What about n equals 50? You're going to do integration by parts for a very long time until you realize that you're actually just generating the same function. The only change is that x becomes p and sigma becomes sigma p. And we realize this by simply writing the equation in momentum space, and we saw it's the exact same equation. The difference is only here in the constants here, right? But that is solved by the energy, right? So if you take, say you go to here, right? You found the phi of x and you found the energies, right? And then you plug in the energies into here. Right? I presented the energies as a solution of this equation. But say you want to plug, if you take the energies, you plug them into here, then you'll see it's exactly the same like this.
So they are the same energies?
No, same energies. Take the energy, En, plug it into here and here, and you'll see that this coefficient is exactly equal to this coefficient. Plug in sigma x and sigma p because they're different. Sorry, don't plug in sigma p, they stay the same. You plug En into here and En into here, sorry, plug in the sigmas as well, you will see it's the exact same equation. So the form of the eigenstates are the same in momentum position space, and of course, again, this only works because the Hamiltonian is quadratic in both x and p. So the two are equivalent. That's basically what I'm trying to point out here. Questions? Okay, before we move on to some problem solving, let me point out a few differences and analogies between classical mechanics and quantum mechanics. First thing I want to talk about are allowed and forbidden regions. We think about a classical particle in a potential well, then what is its motion? It goes back and forth. It oscillates. That's why it's called an harmonic oscillator. It oscillates back and forth. Now it will reach something called a turning point. It will turn around, go back again. So it goes from x to some, let's use something called x naught. I'll call it x0, x naught. That's a turning point. So a turning point are a plus and minus x naught, which means that a harmonic oscillator in classical physics, if it has some energy E, it can go between minus x naught and plus x naught, which means it cannot be beyond this region. Over here, the classical particle cannot exist. But as you know, in quantum mechanics, there's this effect called tunneling. There's the effect that you can be inside a region where the potential energy is higher than the kinetic energy. So the quantum particle can exist there. Before we see this more explicitly, let's just find the turning points in terms of the energy. So in order to find the turning points, what's the deciding factor where something is a turning point or not? You know that at the turning point, the velocity is 0 because it changes direction. It was plus v, it becomes minus v, so it must become 0 in the middle. And where v equals 0, that's by definition the turning point. So at the turning point, you have momentum or velocity equals 0, which means that the energy at that point is just a potential term. When x equals x0, then p equals 0. So this is the energy, and you can solve this equation. You get a plus minus from the root, and there's 2e over m omega squared. So given a certain energy, these are the classical turning points. This is a first year, second week exercise that you should all be able to do. But the quantum mechanic, the quantum particle can be beyond this point. What we're going to do now is actually find the probability of a particle being in the classically forbidden region. So we're going to find the probability of x being larger than x0 or x being smaller than minus x0 for the harmonic oscillator in the ground state. So the quantum harmonic oscillator in ground state, its wave function is, we can look at position space, so we just plug in n equals 0 to here. The only thing you have to know then is that h0, the first Hermite polynomial, the 0th Hermite polynomial is just 1, so it doesn't affect us. So it's just a regular Gaussian with some normalization. Phi 0 of x is the square root of sigma x squared root pi e to the minus x squared over 2 sigma x squared. And its energy is the ground state energy, h for omega over 2, just plug in n equals 0, that's what you get. Now, the probability to be at either x larger than x0 or x smaller than minus x0, right, that's the red region in the drawing, the sketch. This probability is the integral to find the probability of finding a particle somewhere in space is the wave function squared, right? Integral dx. But I'm looking for the probability to be beyond x0, so I didn't take the integral from x0, the turning point, until infinity. So that's all of this region here to the right. And then I need to multiply it by 2, because that's the region on the left. can also have two integrals from minus infinity to from minus infinity to minus x0, and then again from x0 to infinity. But of course, it's symmetric, so I can just solve one integral and multiply by 2. Same thing.
Or 1 minus the integral from...
Or 1 minus the integral from minus x0 to x0. Or 1 minus twice the integral from 0 to x0. There are a lot of ways of doing the same thing. Symmetry is a nice thing. So I'm going to solve this integral, and I plug in phi 0. So we get 2 over root pi sigma x. Integral from x0 to infinity, e to the minus x squared over sigma x squared dx. Now we get stuck because we do not know how to evaluate this integral, right? Because this is some error function which we're going to solve. But if this were a question on the test, this would be the solution, because you cannot solve beyond this without numerical methods. So this would be the solution. This shows you understand physics, right? It's integral of the wave function squared from the turning point to infinity. But if you do know how to solve, well, it's called this thing is called an error function, or it's actually not the error function, it's the complementary error function. Don't worry about what it means. But it's some sort of function, right? And the parameters that enter here are x0 and sigma x. So x0 is the turning point, and sigma x is the width of the Gaussian, the physical extent of the wave function. And if we now plug in, x0, and for E we plug in the h bar omega over 2, the ground state energy, and we plug in all the values of sigma x, we'll be left with a number here. So this thing just evaluates to approximately 0.16. You can do this on a computer, okay? You can check at home that when you plug in all of these values, you're actually left with a number here, and the complementary error function of a number is some other number, and what you'll get is this. So this is 16%. So beyond the numerical complications here, what I'm trying to tell you is that the probability of finding the particle in the red region, where a classical particle cannot exist, there's actually a 1/6 chance, 16%, 1/6 chance of finding the particle in that region. Now note that as the energy increases, the probability gets lower. And why is that? Because we are integrating over a Gaussian from x0 to infinity. Now x0 is proportional to the root of e. So when e is larger, x0 is larger, which means I'm integrating over a smaller area. So this number becomes smaller as e becomes bigger. So we see that as the energy rises, the energy becomes larger, we approach the classical limit. This is something that happens a lot in quantum mechanics, and we'll come back to this principle again in a couple of minutes for a different, something else that also becomes classical at high energy. Questions about this? Let me just add to this drawing of the potential, the wave function. So what I'm saying is that the wave function, right, it's a Gaussian, but it goes beyond the turning points. So it's something like this, just symmetric. So it leaks, right, into the classically forbidden region. And the sum of this area and this area, well, if you take the wave function squared, the sum of this area and this area is 16% of the total area, which is 1. That's the calculation we did. 16% 60% of the area, yeah. But not the area of the wave function, or the area of the wave function squared. Right. Okay. Talk about a little bit about classical intuition. So I have a box, okay? A box, or I have a harmonic oscillator. I have some ball that's tied to a spring that's going back and forth, and I'm covering it. And I would like you to guess, when I uncover it, where will the mass be? At which position? Will it be towards the center? Will it be on the side? Will it be somewhere in the middle? Where would you expect the particle to be in a classical oscillator? So it will most probably be on the sides. Why? Because it's much slower there, right? So think of a pendulum if you want. It spends much more time next to the turning points than it does in the middle, because it rushes through the center, through the equilibrium point with a large velocity, and then hits the sides. When it gets to the side, it slows down. So it spends much more time on the side than it does in the middle. So classically, I would expect the particle to be localized, or more localized at the edges. It's more likely to be found next to a turning point. More likely to be in the vicinity of x0, turning point, plus minus x0. But if you now look at the quantum reality, at least for the ground state and the first few excited states, it's exactly the opposite. Look at the purple line. Where are you most likely to find the particle? And at the middle. This is totally counterintuitive. It's the place where you would least expect a classical oscillator. If I told you I have I'm covering up a quantum mechanical oscillator, and now make a guess where would you most likely find the particle, then you better say right in the middle. So next time someone plays a guessing game, when you ask him whether he's classical or quantum, it's a big difference.
What's the explanation for this?
The quantum mechanics is really weird. Watch this. Let's look at the limit, at the classical limit, right? Look at limit where E becomes large. At large energy, the eigenfunctions, they have this Hermite Polynomial, right? So the larger, that means, so basically n much larger than 1. When n becomes much larger than 1, then the Hermite polynomial becomes a polynomial of high degree, right? N is the degree of the polynomial. Now, before we do this, let's do something else. We'll just sketch out for you the first few eigenstates. So I've already told you that the ground state, it's purple, that the ground state is a Gaussian. Now, first excited state is a Gaussian times a first, times h1, the first Hermite polynomial, which is just x, or 2x. So it's x times a Gaussian. So you get something like this. And the next one up, n equals 2, is a Gaussian times x squared, and then there's a minus constant somewhere in there as well. So what you get is something that looks like this. So notice first of all that the ground state, n equals 0, has 0 nodal points. The first excited state, n equals 1, has 1 nodal point. And the second excited state, n equals 2, has 2 nodal points. Now this should remind you of our discussion that the more nodal points, the higher the energy. We spoke about this during the infinite potential well. We had the same effect. Each higher level added one nodal point. The nth level had n minus 1 nodal points. So here the nth level has n nodal points. That's just the difference because here we start with n equals 0, there we start with n equals 1. But it's exactly the same effect. Also notice the parity, right? So even paired, even numbered are even functions. N equals 0 and n equals 2 are even with respect to x equals 0. And odd numbered are odd functions. Now you also see this peculiar quantum reality for these particles. Well, n equals 1 has 0 probability of being exactly x equals 0, but still the probability of being towards the middle, so either here or here, is much larger than being at the edge, at the turning points. So this quantum reality is true for the ground state and the lower states, for low n. True for low n. But if we look at larger n's, we now have a very large polynomial to a high power. So there'll be way more oscillations, right? The n is the number of nodal points. So for n equals 100, there will be 100 nodal points, 100 times that the wave function passes the x-axis. So it'll oscillate very quickly. Actually, if I make a drawing for you, for, I don't know, 50 or whatever, I'm not actually going to make 50 nodal points, but you understand what I mean? So what this function looks like, use a computer at home and plot it. You know what the function looks like. Just plug in n equals 50. You'll get something that is high, and then oscillates quickly, becomes lower, and becomes high again, and something like this. Okay, so this is not 50, it's more like 15, but this is what happens for for large n. And here when you see, I take this absolute value squared, this reflects the classical intuition. It is more likely to be on the side, the vicinity of the turning points, and less likely to be in the middle. So again, we see the effect that large energy, like we saw here for the tunneling probability, that for large energy we approach the classical limit. This is an important limit of quantum mechanics. Questions about this? Cool. Let's solve some questions.
I have.
Go.
When you draw the 550,
Yeah.
you draw it with accumulating all the previous states, or
Accumulating?
yeah, meaning that you took phi 1 plus phi
No. I took phi n, right,
by its own.
which is hn times phi, hn times x times Gaussian. I took in n equals 50. That's it. It's also the position of all the states. It's just n equals 50. That's what it looks like. I very much encourage you to take out a computer and your favorite graphing program and to plot these functions.
You need to know h.
What?
You need to know h.
Take all constants, h bar, m, omega, take them equal to 1. That's what I do in my notes.
No h bar, h.
What's h? Hn, no. So MATLAB, you just type in Hermite P maybe, and then it'll give them to you. Or just go Wikipedia, find Hermite Polynomials, you get a list of at least the first 10. So I'm sure that's the smallest problem. In the age of computers, we don't even need books to find these kind of things. That's not a problem. Other questions? All right, example, exercise. We're going to talk about something called the Lennard-Jones Potential. The Lennard-Jones Potential describes the interaction or the potential between two ions inside some lattice, inside some solid. So, I don't think, doesn't matter what exactly it is, just imagine two particles, two charged particles, they have an interaction, and the interaction felt by them is described by the potential, which is given by 4v0, let's call this A over R to the power 12 minus A over R to the power 6, where V0 and A are positive constants, real obviously, its potential must be real. A has dimensions of length, V0 has dimensions of energy, so V0 has something to do with the height of the potential, or actually depth. I'll make a plot of it in a second. And A is some typical length scale. So this is given, right? This is the potential between two particles. And R is the distance between the two particles. So we're working in the center of mass frame, where we can just think about one particle moving in a potential. So this is described by a particle moving in a central potential. It's a function of R only. I'll just plot this function. It actually looks like something that you know, which is very familiar to you. It just looks like this. So this is the minus 1 over R to the 6, and this is the 1 over R to the 12. For small r, this is dominant. For larger r, this is dominant. So it looks very similar to the gravitational potential, including the centrifugal barrier, just the powers are different. So this is given. What we want to solve, what we want to find, is the approximate ground state energy of the particles. So one particle. It's one particle. We think of one particle which is, right, distance r from some center, which in this case would just be the middle of the two ions. So you can think of one particle moving in this potential. There's one particle moving in a potential V of r given by this. Let's forget about the stupid drawing. There's one particle moving in a potential V of r, and we want to find the approximate ground state energy of that particle.
R is the central mass R?
Yeah, it's the distance between two particles. That's why you can think about it as one particle. So just don't get confused by the fact between two particles. Every two-particle problem can be reduced into a one-particle problem. That's why it's solvable. And anything beyond that, three particles, is not solvable. Welcome to physics. Okay, so how do we treat this? Solving this exactly in quantum mechanics is impossible. So what we want to do is we're gonna approximate the minimum, right? For the ground state, we know that the particle will be somewhere around the minimum. So we're going to approximate this minimum here by a potential well, the harmonic potential well. And this is just done, this is always possible, this is done by simply expanding V of R in a Taylor series. This is something very general, mathematical, that I'm always allowed to do. V of R, it says the minimum is at some point I'll call R0. So I can expand it around the minimum as V of R0 plus the VDR at R0 times R minus R0, right? Plus 1/2 second derivative at R equals R0 times R minus R0 squared, and so on. This is always illegal to do. Right? It's called Taylor series. It is just theory in math telling me that this is always possible. And because I'm in the vicinity, because the particle is I'm told it's in the ground state energy, so the energy is almost zero, but not exactly zero, because it cannot be exactly zero, it's quantum mechanics. But I know that the distance, r minus r0, is small. So I'm going to neglect all of the orders, order 3 and beyond. And that's why it's called an approximation. I'm approximating because I'm saying this is up to order 2, which is harmonic. Everything beyond that I'm throwing out. Now, V of R0 is just a constant. And as you know, we don't really care about constants in the energy because the energy is always defined up to a constant. So that's just some number we have to find, but it has no physical meaning, no physical impact. What is this term? Actually, this part must vanish, must be zero. Why must it vanish? Because it's the minimum, by definition. So by definition, the first derivative at the point where it's minimal, it must vanish, right? So the first contribution that has a meaning is the quadratic contribution, and that is harmonic. So this part here, right, it's squared, so this tells me that it's harmonic, and the second derivative will be related to the frequency omega. You could say it's related to the spring constant, right? It's actually exactly the spring constant. The spring constant is 1/2 k x squared. Your r minus r0 is actually your x. It's your distance from the equilibrium. The 1/2 is 0 is actually your spring constant. And you know the spring constant is related through the mass to the frequency. So this second derivative is related to the Eigen Frequency of the harmonic well, of the red potential, which I'm using to approximate the real potential. Is this clear so far?
Not really.
Try to phrase the question.
What does the omega mean?
So we're going to find it. We're going to find this omega in a second. First of all, what I'm doing here has nothing to do with quantum mechanics. This is purely classical treatment. And if you haven't done it yet, we're going to meet it in analytical mechanics as well. This is why the harmonic oscillator is so important. Any minimum in a potential can be approximated to be harmonic, because it's the first order that does not vanish. Everything else vanishes, right? And now if you look at the form of a harmonic oscillator, where k is a spring constant here, right? It says 1/2 k v of x squared, right? The x is the distance from equilibrium. So in this question, your x is just r minus r0. That's the distance from equilibrium. And if you look at this term, you'll see that k is actually the second derivative of v, right? And now you know the relation between k and omega, right? So if I find the second derivative at r0, then I can find the omega. That's what I mean by related to omega. Is that clear? All right, moving on. So this is just telling you why the harmonic oscillator can be very important. And as I said, this is a purely classical treatment. There's nothing quantum mechanical about it yet. What do we know from quantum mechanics? From quantum mechanics, we know that the ground state energy is situated h bar omega divided by 2 above the minimum of the potential. Energy of the ground state is equal to some constant, right? It's this point here. It's the minimum of the potential, which in the regular harmonic oscillator case is just 0. That's why it didn't appear there, because the potential was like this, right? So here, V of x equals 0 was 0. So it didn't appear there. But we found that the minimal energy must be a height of h bar omega over 2 above that minimum. So it's going to be this thing plus h bar omega divided by 2. What I'm saying is that the minimal energy is here. This is E ground state, where this distance is h bar omega over 2. It's exactly a height of h bar omega over 2 above the minimum of the potential. It's exactly the same. The only difference is that the entire potential is shifted down in this case versus this case. So what I want to do now is, first of all, to solve this, a couple of mathematical steps. First of all, I need to find R0, I need to find the minimum. Then I need to find V of R0, and then I need to find dV, second derivative, dV dr squared at R0, and from this I will extract omega. So these are our steps to solving. Okay? Questions? Great. We're never going to make it to the end. No way. That's okay. You'll just have to work harder by yourself at home. You're going to hate me for this, right? Okay, we're going to find the minimum. So we take dV dr at R0 equals 0. So the first derivative.
That's 4 or something?
Excuse me?
It's 4 V naught?
Yeah, that's given in the definition. So you get some.
Can we skip it and move to the important stuff?
We will in a second. Not everyone's so smart. I'm sorry. So we take the derivative equal to 0. We find that R0 is equal to 2 to the power 1/6 times A. Sorry, that's not sigma, that's A. Sorry. Plug this back into V of R0. So if you plug in this into the R here, you'll find it's exactly minus V0. So this height here is minus V0. That's why we get a factor of 4 here. It's just easier to think of V0 as the depth of the well. We'll do the same again with the second derivative. So we'll derive a second time. Plug in R0. I will skip the calculation. Sorry, V0 over A squared. All the calculations are online as well. So if you get lost, know that it's all there, and I hope it has no mistakes in it. I really do hope so. Now we can use this relation, right? This is just K, the spring constant. So we take the square of this and then multiply by m, and we find omega. So we get omega equals 6 times 2 to the power 1/3 divided by a root of v naught over m. And then we can plug this thing back into the ground state energy. And there we go. The ground state energy is 3 times 2 to the 1/3 h bar over a times the root of v0 over m minus v0. So we've used quantum mechanics to find the approximate ground state energy of such a particle. It's a potential that cannot be solved analytically. We could use the harmonic oscillator to make an approximation for a ground state energy. This is what physicists know how to do. This is what a big majority of physicists actually do for a living. It's kind of funny, but it's true. Because of beyond that, because the next thing would be to compute corrections. How the real potential actually changes this approximation, but that will be subject of next year, quantum mechanics 2, something known as perturbation theory. Then you're going to talk about how to actually calculate the contribution of higher orders of r to the third and r to the fourth and so on. Moving on to the important stuff. Actually, this is actually very important. This is the physical stuff. Moving on to the mathematical stuff. The mathematical stuff is important because without math, you can't do physics. Any questions about the example that we solved? Excuse me?
I can say what's the R0?
It's 2 to the power of 1/6, 1 divided by 6. Yeah, there's some weird powers in here. That's just life. Not everything are beautiful numbers. Hermite polynomials. First of all, the first thing you know about Hermite polynomials is that they satisfy a ordinary differential equation. Have you met these kind of equations in Math 3 yet?
Yes.
Seen the Hermite polynomials or
Yes.
Legendre polynomials?
Yesterday.
Yesterday, wow, so cool. I'm right on time. Look at me. So I'll help you for both courses, okay? N is a positive integer. A few examples. H0 of x is just 1. You can check that 1 actually satisfies this equation. For n equals 0, h1 equals 2x. h2 equals 4x squared minus 2, and so on. The list is online. These Hn, the Hermite polynomials, are mutually orthogonal. But in order to satisfy orthogonality, we need to use something called a weight function. A weight function. I think it's called weight function. This is almost delta n m. It's up to some constant. That's simply because the Hermite polynomials, for some stupid reason, aren't normalized. Because they're not normalized, we have this constant, and then there's a delta n m. So it equals to 0 when n is different from m. That's what we mean by orthogonal. But they're not normalized, which is why we have this stupid constant, which even depends on n. But you recognize this constant from the wave function of the harmonic oscillator. The reason there's a normalization there that depends on n is because those stupid polynomials are not normalized. So we can blame Mr. Hermite, who apparently was a mathematician, not a physicist, who didn't care to normalize properly. Okay, so this is what happens when the mathematicians do your work. Do it by yourself, it'll all make more sense. So this constant doesn't have to bother you, it's just there because they're not normalized. That's all it means. If you forget about this wave function, and you compute this integral, you will not get the orthogonality. In order to get orthogonality, you have to include this Gaussian. Try it. Of course, it also comes in handy because a Hermite times a Gaussian is a harmonic oscillator wave eigenstate. So that's why the harmonic oscillator eigenstates are orthogonal, because they're some h times a Gaussian, and the other one's also an h times a Gaussian, but the Gaussian times a Gaussian is still a Gaussian, right? So that explains also why the eigenstates are orthogonal. Generating functions. So I'm going to do this without proof. find some of the proofs in my notes, some of the proofs you can find in books, some of the proofs you can find in your math course. You can generate, actually I don't even want to talk about this generating function, I'm not going to need this. Should I mention it? What time is it? Yeah, I'm not going to mention it. Let's continue to how to use these Hermite polynomials in quantum mechanics. One more thing I do want you to note is the parity. H0 is even, right? H2 again is even. You will find that H4, H6, H8, and so on, they're all even. So again, even numbered is even function, and odd numbered are odd functions. Since the harmonic oscillator states are comprised of a Hermite polynomial that has a Gaussian, and a Gaussian is an even function, the Hermite polynomial actually defines the parity of the eigenstates. We already mentioned that the eigenstates are either odd or even, depending on n. So this is where it comes from. Okay, let's solve an example. So we have a particle in a harmonic potential well. It is given by this absolutely general wave function. Where phi n are the quantum harmonic oscillator eigenstates. And En are our energies, h bar omega n plus 1/2. Right, so we found these functions. I still want to write them out every single time. So every time I write phi n, I mean this long function that we had on the board earlier. They're known, right? We want to find the average position for this wave function, which is absolutely general. And we are going to use, we are given the relation, a recursion relation for the Hermite polynomials, namely that the nth polynomial is a superposition or a linear combination of the n minus 1 and the n minus 2 order Hermite polynomials. Yep. So Hn of x, you can check it. Part of your homework is to check this for some of the functions. You can even prove it, that this relation is correct. I'll be there in a second. So Hn of x is 2x times Hn minus 1 minus 2n minus 1, that's the same n as here, times Hn minus 2. This also is very useful because this tells you that as soon as you know H0 and H1, you can construct all the other Hns. Just recursively go through it, work a long time, and you'll get there. So you can construct all of the Hermite polynomials through this relation.
Find what?
Find the average position, x average. Okay, so we want to find an of t, right, as a function of time. Because we're given psi as a function of x and t, so it's easy to find. So let's go ahead. By definition, this is the integral from minus infinity to plus infinity. Then we need to plug in psi star. So there's a sum over n, Cn, phi n of x, e to the minus I e n over h bar t star. Then we multiply by x, we're working position space. And then we put in the wave function again, without a star. And integrate over dx. That looks like a really cool thing to do, right? It's amazing. First things first, we've done this before. I have two sums. the first sum extends only over these three, Cn, phi, and En, and this sum extends over these C, phi, and E. So if I want to shift the stuff around, not get confused, I'll simply switch the second n to an m. Now I'm confused. It's a dummy variable. This is always legal to do. So let's take the complex conjugate of the first, shift everything around. So there's a sum over n and a sum over n. Cn star Cn. Then there's an e to the I En minus Em divided by h bar. Notice the sign change of En due to the complex conjugate. And then there's an integral of phi n times x times phi m dx. I do not need a star on the phi n because I know they're all real. This is not true in general, but for the harmonic oscillator we saw that all the eigenstates are real. There was no I in the eigenstates, so I'm just not going to write the star. Now this thing here, this integral, it looks like an average, but it's not. If this were phi n and this were the same phi n, this would be the average position of the nth eigenstate. But you see I'm using phi n here and a different phi n here. So this is not an average. This is actually something we call a matrix element. For reasons that will become clear a few weeks from now. But just note that we call this construction, which looks like an average, but it's not because we're using two different eigenstates. We call that a matrix element, and we'll just symbolize it by x, like the average, but we'll use a subindex nm to remind ourselves that we're using different functions. Another way of writing this using our this notation with the brackets. Where am I? This notation where we have the x operator, which is this multiplication by x, and as you see, there's a phi n and there's a phi m. So a different wave function, which is why this is not an average. It's something we call a matrix element. As I said, for reasons that will become clear a couple of weeks from now. Just wanting to hear the name now already. Okay, so let's compute this matrix element. Let's plug in the eigenfunctions. So there's some normalization constant, and then there's the h, right? The Hermite Polynomial, and then there's the Gaussian. So the matrix element it's going to get long, okay? Just plug it in. It's that simple. There we go. So there's an x. That's what we had from the average. Then there's an hn times a Gaussian and an hm times a Gaussian. This Gaussian has no 2 in the denominator because it's a Gaussian with a 2 times a Gaussian with a 2. That's a Gaussian without a 2, right? It's a sum. Now we'll change variables just to get rid of this sigma x. I'm going to switch to y, which is not the y coordinate, right? It's still a one-dimensional problem. Y is now some dimensionless parameter because x is a length and sigma x is a length. So it's a dimensionless parameter. I'll just get rid of all of these stupid arguments. But it'll take out a sigma x when I replace this x, and also one from the dx. And one of them will go with this sigma x. So what I'm left with after I do this change of variables is sigma x divided by this square root. And then there's an integral from minus infinity to plus infinity. There's the same orders of the integral. There's an hn of y times an hm of y times e to the minus y squared dy. Now you see exactly why I did this. Right, it's starting to look. There should be a y in here as well, you're right? That's what messes up the orthogonality, right? So there's a y as an hn times hm times e to the minus y squared dy. Okay, we're getting there. Let's plug in this relation, the recursion relation. Obviously, I'll be using it with y, not with x. Just think of there being a y here instead of an x. Of course, the same thing. So if I plug that in, space. What's the time, by the way? How bad am I doing? 1 minute. Yeah. So I'm gonna ruin your weekend. Okay. I'll give you. No, I'll take more time now, and then next week you won't do lesson. Okay. I'm giving it to you. No lesson next week. Okay. Okay, so what are we doing? Why is this so good? Why is this so good? Wait a minute. Why is this so good? Because we're going to use this relation, but we're not going to use it for n. Sorry, we're going to use it for... Right, what we're going to do is replace n by n minus 1. So we can take this relation, right? We'll write it with y, and then we replace n goes to n plus 1, just advancing the index by 1, which of course is also legal to do. Just a dummy variable. I could call it n plus 1 and then change n back into m, right? And so what we get is y times hn of y equals 1/2 hn plus 1 of y plus n times hn minus 1 of y. Okay, so instead of having n minus 1, n minus 2, and I have n plus 1, n minus 1, right, because I advanced index by 1. And you see why it's so useful, because this y times h is this y times h. So this way I can get rid of y times h and express it just in terms of h's. And then I'll be able to use the orthogonality condition on the hns. So let's do that. So we get this constant. It's the same square root again, okay? In favor of your weekend, I won't write it down again. So there's an integral of minus to plus infinity. And now instead of yhn, I write this. So there's 1/2 hn plus 1 of y plus nhn minus 1 of y. And then it's multiplied by hm of y times e to the minus y squared. Now I can use orthogonality, dy. So after I use orthogonality, I get sigma x. There's going to be a 2 to the m's. This is from the orthogonality. Remember, it's orthogonal up to a constant. This is the constant from the orthogonality. The root pi went away with the root pi in the denominator. And then we get 1/2. So hn plus 1 times hm is a delta n plus 1 m. Then And then Hn minus 1 times Hm times the Gaussian is delta n minus 1 m. So it's either equal to 1 times some constant, if n minus 1 is equal to m, but if n minus 1 is different from m, it's 0. That's just what I'm expressing here. There's some mixing between the plus 1. Expression. Now, what can we do with this? Why do we do all this? We can take this expression, the matrix element, and plug it back into the average of x. Remember, the matrix element was something that appeared inside the average of x. So the average of x is some double sum with some coefficients times the matrix element. So now we found the matrix element. This is this thing here. So we'll take this matrix element and plug it back into here. And then, because of a couple of deltas, and we have a sum, so we can take the sum, say, over m, and get rid of the delta functions. That's the reason we love delta functions, because they kill sums. We're almost done, I promise. So we'll plug this in. We get a sum over n, sum over m, Cn star Cm e to the I En minus Em. T, and there's a sigma x 2m, sorry, 2 to the power of m, m. You see, if Hermite would have normalized his functions, we would work much less. So it's not my fault, you can blame him. Actually, we should probably write, it's even n, doesn't matter. In a moment, all n's will become m's or n minus 1 or n plus 1s. So this is a sum. There are two terms, right? There's the term with this constant times the first delta, and then there's the one with the second delta. So there are two terms, and in one of the terms we have to replace all of the m's by n plus 1, and in the other term we have to replace all of the m's by n minus 1. Right? First term, replace m by n plus 1, and the second term close m by n minus 1. That's what summing over m with a delta function means. That's how it's done. It's the definition of a delta function. Picks out the value. So after doing all of the algebra that is left here, and I'll also plug in, I'll skip a couple of algebra which can be all found online. I'll also plug in the Eigen Energies. That's obviously going to be useful because you see you either have m equals n plus 1 or m equals n minus 1. So you either get En minus En plus 1 or En minus En minus 1. So the difference between adjacent energy levels, which you know, which is h bar omega. So after I do all of that, I get sigma x divided by 2, sum over n, Cn star, then there's a root n plus 1, Cn plus 1, e to the minus omega t, plus root of n, Cn minus 1, e to the I omega t. Beautiful. So all of that mess becomes this, also a mess, but as big a mess. But you see that the average of x is, right, you take the coefficient, you multiply it by the one of the next eigenfunction, or by the one beforehand. There's some constants that have to do with normalization. These are Hermite's fault. obviously the length, this is all dimensionless. So the units only cover the sigma x. As I said, that's the length scale of the problem. Every length in harmonic oscillators will always be a sigma x times some number. You can always express it that way. So yeah, if you know your initial function, then you can just plug in your Cn's. Given psi x of t, plug in all psi n's, and then you find your x of t. It's a very general equation, but it's a nice exercise because it demonstrates how to use sums, and demonstrates how to use recursion relations, and demonstrates how to use orthogonality relations. Questions? When can I go home? Now we can go home. No more questions? Okay, so have a happy Hanukkah, and I'll see you in 2 weeks.